So the last type of reaction that we're going to discuss is double displacement reactions. And like the single ones, the word replacement is also an acceptable description. So don't let that be a barrier, those different words be a barrier to identifying what we're talking about. So double would imply two. So in double replacement reactions, you have two ionic compounds that exchange partners. So they switch with each other. And in the switching, if one of the new combination produces a gas or a solid, then there will be a reaction. So let's think, what are we talking about? Switching, and then we're going to look, I have 3 examples where we can actually work it through. So the switching, and this line right here is in A's and B's. It's a predictable pattern, how they will switch. So what will happen is ionic compounds are always a positive followed by a negative. That's the compound. So if one of them is a positive and negative, and then the second one up here in the corner I'm writing a positive and a negative, what happens is this positive will switch with that negative, and this positive will switch with that negative. And that's always the pattern. So looking down in the middle of the page where I have the A's and the B's and the C's and the D's, the A will always take a look at the D. That's where you see this. And the C will always go together with the B. Now, we write the C first because it is the cation. So even though we're rearranging them on the other side, the cation, the positive one, the metal, always has to be written first. So now let's take a look below it and see the switching pattern. So here is lead, which is the metal. And so it will take a look at the iodine, which is the second one. So the 2 outside ones look, and we see that it forms lead iodide. And then the potassium, the positive one here, will get together with the nitrate, and we see this here. Now, just like in the last ones, we're going to have to use the ions or the charges to predict, oh, I can't even spell, predict the new formulas of the compounds. Okay, now how we get the S and the AQ, here we use the solubility chart. Okay, so this is a different chart. So in your exam, in class, I'm going to give you 2 charts. There's an activity series. That's the one where you have the metals and the halogens in a line. And we use that because we know if a metal is above another one on the chart that it will displace it or replace it. And here we use, I've got to get to it on your page, a solubility table. Okay, so we're going to put things together, and by looking at the solubility table, we're going to figure out, are you going to stay a solution and be aqueous, or are you going to make something that is a solid? And so if you look down here, you see what it means. So AQ, there's lots of AQs, means you're soluble, you're aqueous, you're soluble in water. Slightly aqueous. We won't really do anything with that, but you see some of them are only slightly. The other one that we'll be interested in is the I. So insoluble means that you will form a solid. And if a solid is formed, that is one way we'll know that a reaction happened. Okay. There's also a D that decomposes in water. That's one of the ones that goes to form gases and things. We will not be worried about forming gases, only about forming solids. Okay, so let's go and see how we would use the solubility chart and complete an equation. So here's an example, and you're going to have an example like this in your lab. So the pattern, and let me just show you, is the first one in this formula, the cation, H, is going to go with OH. And then Na is going to go with I. So that's where they're going to switch. Now, in order to know how they're going to get together, we have to know their charges. H is a positive ion, okay? And then it's going to go together with OH, which is hydroxide ion, which is a negative. So then H, it's a +1, -1. So this is one I wanted to point out to you. It's HOH, which is actually water. So when H gets together with OH, it makes water. So we'll have water, which is H2O, and it's not AQ, it's L. Okay, so that's a new thing. I don't have to look on the solubility chart because I make water, which is a liquid. And it's interesting, but the formation of water is a chemical reaction. And now let's look at the other ones. And I have, let's see, Na. So Na is a +1. And then iodine is a -1. So it is 1 to 1. So it'd be plus NaI. Now we can look on the solubility chart and see what we would put for this one. So you'd find Na, which is right there, and I, which is right there, and you see where the two meet. And so that is aqueous, which means they're going to be dissolved in water. Now, I'm going to erase these little lines and let's make sure it's balanced. I see that all the ions, like right here, are +1 and -1. So I don't think it's going to take any coefficients because I think they all switch equally. So let's see. I'm going to do my sodium first because I like to do metals. So sodium 1, okay? Iodine 1, iodine 1. This is one people mess up on. There's 2 hydrogens, and then there's 2 hydrogens. And then there is 1 oxygen and 1. So it is balanced. Okay, so what we have to do just in summary, and we're going to try 2 more, but in summary, we look at our reactants, which are ionic, so they have a positive and a negative part, and we switch them, and it's always the 2 outside ones are going to form something new, and the 2 inside ones are going to form something new. And what we're looking for is a combination that forms a solid or a precipitate. So let's go ahead and try the next one. So this is, write the balanced reaction equation between potassium carbonate and barium chloride. And when I think I typed this one, and I did not put that they were solutions, but they all are solutions. So they all start out as aqueous. Now this brings up something that I want to tell you, which was true in the previous slide, but I'm trying to just kind of give out the information. Ionic compounds, when they are dissolved in water, they do what I call the D word, they dissociate. Now, dissociate means that they separate or fall apart into their ions. Okay, so for example, I'll just write down here, if you have sodium chloride and you've dissolved it in water, you no longer have actually table salt like sodium chloride. You have sodium ions and chloride ions. They dissociate. If you had magnesium and chloride ions dissolved in water, they dissociate into magnesium ions and two actually chloride ions, right? Because magnesium chloride has two, so it will separate into the two chloride ions. So the reason I mention this is when we place solutions together, they're actually just a bunch of ions floating around, and so that's why new ions come in contact with each other. And if they come in contact and they form a solid, then you have a reaction. So let's look at this one. We have potassium carbonate. So I need the ions to write the formula. Potassium is a +1. Carbonate is a polyatomic ion, so that's its two ions, and it would be K2CO3. And we're going to react that with barium chloride, and barium is a 2+, and chloride is a halogen, it's a -1. And so we're using some of the skills that we acquired in chapter 11 and in chapter 6, putting together formulas and things like that. So those are my two reactants. Now what's going to happen is potassium is going to go together with the chloride ion, and we see that potassium's a +1 and chloride's a -1, so that would be KCl. And let's look and see what it is, if it's soluble. Okay, so let me erase this. So K is here and Cl is here. So it's aqueous. In fact, if you look, everything with potassium's aqueous, everything with sodium's aqueous, like everything with nitrate's aqueous. So there's several things. If you see the ion there, you know it's aqueous. So this is aqueous. And then we have barium and carbonate. And we're going to put the barium first. So because it's positive, and it's a 2+ and a 2-, so it's 1:1. Okay, so there's that formula. And let's look and see about barium carbonate. Okay, let me erase some of this. So barium is right here, and carbonate's here. So if we look, it has an I, which means insoluble. And what that means is it forms a solid because it won't dissolve. And so we put S. So S doesn't mean soluble. S means solid. So this, if you put potassium carbonate and barium chloride together, they will form a solid. Barium carbonate is the solid. Now we call this right here, the potassium and the chlorine or chloride, spectator, are called spectator ions because if you're aqueous, it really means you're dissociated. And so the potassium and chloride ions were a part of an aqueous compound in the reactants and in the products. So they're not doing anything. What the reaction here is barium reacting with carbonate ions to make a solid. Now, this is not balanced. Let's look. So, okay. So I'm doing my potassium first. I have 2 on this side and 1 on this side. So I have to multiply it by 2. So I'm going to put a 2 here. And then I'm going to do my barium next, because I like to do my metals. There's 1 on this side and 1 on this side. Now, I am going to do carbonate all together, CO3. There's 1 on this side. These reactions are really easy to do, the polyatomic ions together, because they stay together as they move around. So it might help you see it. And then the chloride ion, I have 2 on this side and 2 on this side because I added the 2 here, so there's also 2. So this is the final answer for the balanced chemical equation. Okay, so let's do another one, and then you'll get to practice. For this one, we're doing 4 different double replacement reactions in lab. And so you'll be able to predict the products. And then I hope when you start to see what solids form and stuff, you'll be able to connect the solids in your test tube to what the chemical equation says. All right, so here's another one. Let's do this last one. And I have some other examples in the video lessons if you want. Or again, these are the kind of things you could Google and look online to find more examples. Okay, so ammonium chloride. So ammonium is NH4 plus and chloride is Cl minus. So it's 1 to 1. And then sodium nitrate. Sodium is Na plus. Nitrate is NO3 negative. Again, 1 to 1. And it tells me their solution, so they're all aqueous. Now, if I'm switching partners, the ammonium, the positive one, always goes out here with the negative one. And then sodium's going to go with chlorine. So ammonium with nitrate would be 1 to 1. So NH4, NO3. And let's check what it is. NH4. I already told you everything with NO3 is aqueous. So that's aqueous. Plus NaCl. So look back. Whoops, I looked forward. NaCl. That's also aqueous. And so here is something. This is no reaction. So we didn't even have to write the whole thing. And the reason is both products are aqueous. So remember what aqueous means. When things are aqueous, that means it dissociates and the ions separate. And so if all the ions are separated on this side, so like it's aqueous, aqueous, and then they stay aqueous and aqueous, then everything is just floating around and not doing anything. So for a reaction, we need an insoluble, product. So we need that would be an I on the chart, but a solid. Or it could be a gas. But again, I'm going to test you over if they form a solid. I won't give you an example that forms a gas. All right. So that hopefully will get you started thinking about these reactions. We will practice them in lab, and if you have an opportunity, look at your homework or look at some examples and see if you can do it, or if not, let me know and I can help you.